this video, we introduce hypothesis testing with the idea of the permutation test. So let's imagine we are interested in studying two groups of people and seeing how much they pay for textbooks. And these two groups of people are biology majors and sociology majors. So we suspect that biology majors, on average, pay more for their textbooks each semester compared to sociology majors. So that's our big research question in English. And in statistics, we can write this down as a null hypothesis that mu b, or the mean amount that biology majors spend on their textbooks in this semester on average, is equal to mu s, which is the mean amount that sociology majors spend on their textbooks in a semester. Our alternative hypothesis is that biology majors spend more than sociology majors. So the way that we can test this null hypothesis against the alternative hypothesis is by looking at a randomization-based hypothesis test, which is called a permutation test. So imagine that we have this data. Here's biology majors. Maybe imagine that we sampled more, but for the purposes of this demonstration, we just have 4 data points for biologists and then 3 data points for sociologists. And remember, if the two groups are just the same, if they have the same mean, then that means that this number 320 could have just as easily come from a sociology student as it did from a biology student. And similarly, if the two mean amounts of money spent on textbooks each semester is truly the same between the two groups, then this 180 could have just as easily come from the biology group as from the sociology group. So this is our original data, and if we go crunch these numbers to find the average, the X bar for the sociology group is $360, and X bar for the sociology group is $220. Now, there's our original mean for each group. Now we can think about shuffling this all up. So what we're going to do is repeat a process a whole bunch of times, maybe like 10,000 or some other large number. And we're going to go through and just shuffle these up and choose 4 of these at random to be biology and 3 of them at random, and the remaining 3 will then be sociology. So perhaps maybe we go through the first time, randomize, and we find that these 4 numbers are for the biology group, and the remaining 3 are for the sociology group. Then we could go ahead and crunch the numbers and find that X bar for the so-called biology group would be 320 plus 480 plus 260 plus 220 over 4, and X bar for the sociology group would be 180 plus 290 plus 350 over 3. Okay, so from our original data set, there is a $140 difference in these two means. So X bar B minus X bar S in the original data set is 140. So this is a special number. We're going to hold on to this original test statistic, or this original difference in means, and then compare all the simulated differences in means against this. So we'll go crunch these numbers and record it, and then we'll repeat this process maybe 10,000 times and get a whole distribution of these differences in means. So in the end, maybe our differences in means will have a histogram that looks something like this, and maybe 0 is over here. And then we can test to see where does 140 line up compared to, actually, sorry, 0 should be like here. where does 140 lie in comparison to the rest of these simulated test statistics? So this is a histogram of simulated test statistics. Then we go and look at 140. Where does 140 fall? Maybe 140 is right here. And we can calculate the proportion of test statistics as extreme or more extreme than 140. And that proportion of test statistics will be our p-value. Pausing for a moment, why did we choose to shade in the right tail and look for the proportion greater than or equal to 140? That's because we set our alternative hypothesis to be mu b is greater than mu s, which is the same thing as mu b minus mu s is greater than 0. So we, because this is greater than, we need to find evidence that supports the alternative hypothesis, which is saying that biologists spend more money than sociologists on textbooks on average in a semester. And this is the direction that would indicate biologists are spending more on average than sociologists. So we look at that upper tail to find our p-value. So the big thing to see here is repeat this process of shuffling up your data a huge number of times. And each time that you do this, make sure you keep your original sample sizes. So originally we had 4 biologists and 3 sociologists. So we keep going through and randomly select 4 to be biology, make the remaining 3 sociology. Calculate the sample mean for the biology group, calculate the sample mean for the sociology group, find the difference, record it in the histogram. Then we go through and do that again. Randomly select 4 of these to be biologists, the remaining 3 are sociologists, find the 2 sample means, find the difference in them, and stick that into your histogram. Do that a huge number of times to build up a nice detailed histogram. Then go and compare your original difference in means against what we find here in the simulated differences in means. And intuitively, if your alternative hypothesis is correct, then you'll end up with a test statistic that's pretty far over to the right in this case. We'll end up with a test statistic that's pretty extreme, and that will produce a small proportion of simulated test stats that are greater than or equal to the original test statistic. So that would give us a lot of evidence to reject the null, which is the 2 means are equal, in favor of the alternative, which says that biologists spend more than sociologists on average over the course of the semester on textbooks. All right, so that's our permutation test. It's called permutation test because we are permuting the data between the 2 groups. All right, so that is how this works. We'll talk about this more in future videos.